Okay, the next topic we are going to discuss is how do you formulate an equation when you have multiple materials. So in this case, we have a node which is on the boundary between two materials. It says K1 and K2. In reality, we have KX1 and KY1 and KX2 and KY2. So it's both heterogeneous and anisotropic. We've also accounted for different node spacings in the two materials, delta Y1, delta Y2. We're assuming a uniform delta X in this case. And so this is probably the most complicated formulation thus far. So how do we go about solving for an equation for the head at node I in this case? What we do is we create two sets of imaginary nodes. So this, what's shown on the left represents a recreation of this node from the perspective of material 1. So if you look at the spacing between here, delta Y1, if you look at this material, if you consider an imaginary node down here, the same spacing as A is, we'll call this imaginary node B1. The subscript 1 means it's associated with material 1, and we have delta Y1 and delta Y1. So this distance to B1 is the same distance we have to A. And then likewise, if we look from the perspective of material 2, and so in this case, we're going to take the spacing that we have here, and we're going to put a node, an imaginary node up here in material 1, which we're going to call A2, and it'll be a spacing of delta Y2. Okay, so now that we have that, for material 1, we're going to go back to, and this is precisely the same equation that we derived for anisotropic materials in the previous video, just immediately prior to this, where we talked about how to deal with anisotropy. And so this is an approximate second derivative in the x direction, and this is an approximate second derivative in the y direction. So this is our basic finite difference equation from the perspective of this configuration here. So it has B1 and KX1 and KY1. Okay. Then for material 2, we do the same equation, but it's using KX2 and KY2, and it's using delta Y2. So we basically just formulated that fundamental finite difference equation, which uses approximate second derivatives for each of these two cases using the imaginary nodes. And then the next thing we do is we note that the flow rate in the vertical direction is equal. So what does that mean? That means as you're flowing vertically, this is like flowing perpendicular to layering through multiple materials that we discussed earlier in our earlier videos earlier in the semester. And remember, in that case, the flow through material 2 has to be the same as the flow through material 1. The water has to go through both materials, and it goes through the same rate. Now, if you're going in the horizontal direction, the flow will partition between material 1 and material 2 based on the hydraulic conductivity and the geometry. But in the vertical direction, you have to have the same flow rate. So if we say Vy1 is equal to Vy2, and then we use the Darcy's law representation of the Darcy velocity, and so that would be so K. Let's go back to this. So K. Up here we have HA minus HI divided by delta Y1. And for down here we have HI minus HB divided by delta Y2 for our hydraulic gradients. And so here are our equations. We have ky1, ky2. So this is just continuity using Darcy's law. And so this gives us three equations. This is 1, this is 2, and this is 3. And we're going to skip a bunch of steps here. But if you combine these three equations, you can eliminate the two imaginary nodes that we created and reduce this to a single equation. So there we have it. This is, like I said, this is the most complicated of all the cases we have thus far. So this is the again, for the interface between two materials, we have, and it has anisotropy. We have kx different than ky. We have different spacing. So this is the most general equation. It encompasses all the different combinations you could have, including multiple materials. And so that's how you'd go about formulating that. If kx is equal to ky and delta x is equal to delta y, then now we just have k1 and k2, in which case it reduces to this equation, which is very similar to what we had before, but now we add on these two, 2k1 over k1 plus k2 and 2k2 over k1 plus k2 in front of HA and HB. And yeah, that's the simplified version of that equation with multiple materials.